All right, welcome everyone. Today we got another series test. This time the root test. So it's another one of our series tests to determine whether a series converges or diverges. So whether the sum exists or whether it doesn't exist. And it's gonna feel pretty similar to the ratio test in some respect. So let's take a look at it. All right, so here's the test. So we're given a series, sigma an, and we're going to, in order to actually perform the root test, well, we're going to look at the nth root of the absolute value of an. And we're going to do the limit of that as n goes to infinity. So, pretty well named test here. We're doing the nth root. It's called the root test. And so we're looking at this limit as n goes to infinity of the nth root of the absolute value of an. And we look at what that limit is equal to. So if the limit exists and is less than 1, then the series is convergent. Actually, it's a little bit more. It's absolutely convergent, but we're going to see what that means in a future lesson. So right now we're just thinking if L is less than 1, the series is convergent. If L is greater than 1, or if that limit is infinite, then the series diverges. And if L is equal to 1, then the root test is inconclusive. So these three statements here are very similar. Well, they're exactly the same as what we saw with the ratio test. So just to make a little note of that here. These are the same three statements. So, kind of one less thing to memorize here, because if you have it memorized for the ratio test, well, it's the same three statements regarding that limit L. All right, so what we're actually doing here with the root test, though, is different. So we're computing the limit of the nth root of the absolute value of an. That's different from the ratio test, but these conditions are similar. So if L is less than 1, we have a convergent series. If L is greater than 1 or is infinite, then we have a divergent series. And if L is equal to 1, the test is inconclusive, meaning we don't know what it's doing. So the series might converge, it might diverge, we just don't know. We would have to use some other test. All right, so let's try an example. And generally where we would use the root test is something like this first example. And what do we see? Well, we see n raised to the power 3n. So we see this exponent n here. And then in the denominator, we see the same thing. We have 2n plus 1 raised to the 3n. So we see it being raised to the power n here as well. So generally, we use the root test when everything is being raised to a power n. So to really emphasize that, we're going to rewrite this series. So the numerator here has this raised to the power 3n. The denominator has this raised to the power 3n. So we can actually kind of use one of our exponent rules and sort of factor off that common exponent. So we could really write this as n over 2n plus 1 all raised to the power 3n. And so these are the types of series that the root test really works best for when everything here is being raised to the power n. So that's where the root test generally works better. The ratio test is still our kind of our go-to test. The root test can be helpful, though. We tend not to use it as much, but it can be helpful if everything is being raised to the power n, and in some other cases, but especially where we have everything being raised to a power n. All right, so let's actually see how the root test works. So we're going to start off just by looking at the nth root of the absolute value of an. And now when we say the nth root, one of the usual things we do, whether it's for differentiation, integration, is we normally rewrite the root sign. So that can be helpful here. So let's rewrite this root sign as raised to the power 1 over n. And then let's write in what the absolute value of an is. It's just everything here. So it'll be the absolute value of n over 2n plus 1 raised to the 3n, and then the absolute value of that whole thing. Now, a lot of times with series, and in this case with this series, is everything is positive here, so we could really drop the absolute value. If we had sort of one of those alternating terms, a -1 to the power n or something like that, then the absolute value would just cancel off the negative. But here everything is positive, so we can just drop the absolute value sign. All right, so let's do that. So we'll have n over 2n plus 1 raised to the power 3n, and then that whole thing raised to the power 1 over n. So we've just dropped the absolute value sign. And now we have something raised to a power 3n, and then that whole thing raised to another power, 1 over n. But what do we do when we have multiple exponents like that? Well, we multiply them. So that's one of our exponent rules. So we just multiply those exponents together. So we have 3n times 1 over n, the n's cancel. So we're left with just n over 2n plus 1 raised to the power 3. So we've just multiplied the exponents there. And that's an exponent law. All right, so here's our, we know with the root test, we're interested in this nth root of the absolute value of an, and we've done it, we've simplified it down. Now we actually have to go through and calculate the limit. So, the first step here might be just to get this thing set up and simplified. The second step is to actually do the limit. So we're going to do the limit of the nth root of absolute value an as n goes to infinity. And let's put in our simplified version. So let's use our simplified version here. So we're going to do the limit of n over 2n plus 1 cubed as n goes to infinity. Now we have this thing being cubed. The cubed function is continuous. So we can bring this limit inside the cube function. So that's a continuous function. We'll call it what we want to call it. The cubed function, or raised to the power 3. But whatever it is, whatever you want to call it, it's continuous. So we know limits behave nicely with continuous functions as long as the limit of what's inside exists and the function's defined there. So this is a continuous function. We can bring the limit inside that cubed function. And now it comes down to just doing the limit of this rational expression, n over 2n plus 1. And we go to our usual strategy for that. So we look at the highest power of n in the denominator. In this case, it's just n. So we divide everything in the numerator by n, everything in the denominator by n. So it's our usual 1 over the largest power technique there. All right, so let's apply that method. And the limit is inside the cubed function. So we'll get n over n divided by 2n over n plus 1 over n. So we're just going to our 1 over the largest power of n method there. Simplify this. And it's still inside the cubed function, so we get 1 over 2 plus 1 over n as n goes to infinity, all cubed. And then actually calculate the limit, and we know this 1 over n term, that goes to 0. That's our c over infinity form. It goes to 0. So this ends up being 1/2 cubed. And ran out of space there, so we'll put it underneath. So this ends up being 1 over, well, maybe we'll say a little bit more. 1 over 2 plus 0 cubed, which simplifies to just 1/2 cubed, or 1 over 8. So that's equal to 1 over 8. So what does the ratio test, or the root test actually say then? Well, let's state our conclusion. So we kind of went through the setup here, apply the nth root, simplify, clean things up, then do the limit. So here we, went through our our usual limit routine. We had a continuous outer function, so we were able to bring the limit inside. Then it was just a rational expression, so we used our usual technique there. We got a number. So we were able to calculate this limit and get a number. So then you just state your conclusion. So since, how do we want to say this? Well, since the limit is equal to 1 over 8, which is less than 1, what does the test say? So we calculated the limit L. It was 1/2 cubed, or 1 over 8. It's less than 1. The series is convergent. So we state our conclusion. And then we want to state the test that we actually used. So by the root test. So there we go. That's really how this works. So the root test is most helpful when we have everything being raised to a power n. All right, so, and that's what we have here. So just a little note, really stress this. The root test works best when you can write the series in the form, you have your series that you're interested in, you can rewrite it where everything is being raised to a power n. So that's what we did. Going back to our example here, we had this series that we were interested in. We were able to rewrite it where we have something being raised to a power n. We actually had 3n here. It's still the same idea. So that's where the root test really works well. And we also have this same disclaimer that we saw with the ratio test and the root test. So both of them have this same inconclusive condition here. So if the limit L is equal to 1, then both the root test and the ratio test are inconclusive. So again, what that means, it doesn't mean that we can't answer what's happening with the series. It just means that those tests don't work. So we would have to use some other test. So if you're going through and you get L is equal to 1 for either the root test or the ratio test, doesn't mean you can stop. Just means those tests don't work. They're inconclusive. You'd have to go and try something else to determine whether the series converges or diverges. And one other little note here, this one's worth kind of starring here. If you go through and the root test is inconclusive, well then don't even try the ratio test, because that would be inconclusive as well. And the opposite is true. So if you're going through and you try the ratio test and it's inconclusive, don't waste your time. The root test is going to be inconclusive as well. So these two kind of are very similar, and if one's inconclusive, the other one's inconclusive. All right, so that's really it for the root test. So we're not going to use this one too much. Really, again, it works well when we have things like this, something all raised to a power n. All right, so next time we're going to kind of look at, I guess it's one more test. Maybe we'll call it a test. But it's this idea of absolutely convergent. So we're going to investigate what this means next time. So we'll see you then. Bye-bye.